Hello, everyone. So, this talk is about how Spotify outgrew its service discovery shoes and how we went about finding a new pair of shoes. And instead of 1 million DNS shoes, we now have 1 million XDS shoes. This will all make sense. Just give me a minute. Yes. So, we'll cover what problems we were facing and why we ended up designing around XDS, design and implementation choices, and how we transparently rolled this out without any adverse effects. There's an asterisk here after that, but I'm sure we'll get to that as well. I'm Erik. I work as a staff engineer in Spotify's core infrastructure product area. And with me I have Erika, who's a senior engineer and subject matter expert in our service networking team. So first off, a little technical context about Spotify stack. So it's a microservice architecture that runs on GKE. We were originally on-prem and moved to GCP in, I think, 2017. The first running VM with the custom orchestration, and first we were running on VMs with a custom orchestration layer, and then, then we moved to GKE and Kubernetes. The majority of services are written in Java and using an in-house Java framework, but there's also a smaller set of services written in other languages like Python and Node.js. And we're really big. You can see some numbers on the slide here that should give you some kind of sense of scale. Most of the service-to-service traffic is gRPC, I think 75%, give or take. And then we use Proxyless gRPC, which means then that gRPC clients connect directly to servers as opposed to traditional service meshes where that might make use of forwarding proxies and sidecars. 25% of the traffic that remains after gRPC is a proprietary protocol which we're migrating off. And while most of our internet ingress is in HTTP, there's very little HTTP that goes between services. What else? We're deployed in 5 GCP regions, and we have a regional failure domain where each region can provide most of the end-user services independently. But it's possible for services to make cross-region calls, for example, when a service has a regional outage or if the service isn't deployed in all regions, which happens for our smaller services. So here's a basic sketch of Spotify's service discovery system. It's called Nameless. It was created in 2013 to replace a bunch of bash scripts that were managing DNS zone files. And why it's called Nameless, we don't remember. The same system has been in use since the on-prem days and has been updated over the years as Spotify's infrastructure has evolved. It has several internal components supporting heartbeat-driven service registration, which is used by the workloads that we had that are still on VMs. It controls regional redirects on a per service and per protocol level, and then it subscribes to endpoint slice changes in our Kubernetes clusters to provide service discovery to services running in Kubernetes. The component that does this Kubernetes business is a later addition to Nameless, and we call it Shameless. I thought you might enjoy knowing that. So. Service discovery data then is exposed as DNS SRV records using core DNS, which is queried by services through normal DNS infrastructure. In our case, Cloud DNS and a few custom resolvers. Since we have a regional failure domain, our service discovery system has no interregional dependencies and operates independently. Excuse me. All right, so we're hitting some limitations with DNS. We're running into DNS response size limits for our largest deployments, where a DNS response would exceed the maximum response size of 65 kilobytes. Plus, DNS adds uncertainty to the system. The time it takes for a service to unregister becomes difficult to reason about when there's DNS caching at multiple layers going on. One-way communication is quite limiting, and combined with the inflexibility of DNS, it makes it very difficult for us to build any advanced routing features that we're starting to require. But on the other hand, our DNS-based system has some benefits. It's robust and battle-tested. It's been around forever. It's simple. It says relatively simple in parentheses here, but it's well supported by a lot of clients, and it took Spotify this far. So we're not kicking it out. There will always be some legacy and third-party services that need basic DNS service discovery. And we're also using DNS as a fallback, which Erika will talk more about later. Right, so to pick a successor on how to solve our service discovery problem, or what kind of shoes to get, I think there was some shoe metaphor in the beginning. We took a structured three-step approach to assess our options. And we started with a set of requirement criteria where we assessed our capabilities, we assessed the capabilities of market-leading service mesh solutions, and also included in that the idea of expanding our existing infrastructure. Then we estimated the effort it would take to bridge any gaps in solutions that didn't meet the requirements. And first up then was to find the set of criteria that we thought was most important. And we were considering mainly stuff around reliability, scalability, and extensibility. So for example, it needed to support Proxyless gRPC. We had to be able to configure zone-aware load balancing, and it needed to fit the heterogeneous service architecture we have at Spotify. So after that, we picked which candidates to evaluate, and we looked at Traffic Director, which is a Google managed control plane, and we have extensive experience with GCP's Traffic Director from experimenting with it at Spotify for some time. But this experimentation has surfaced several aspects of the product that were incompatible with our service network and our needs. But since we already knew that it wasn't a good fit, we also evaluated a variant where we would bridge this product gap using a custom proxy layer in between TD and our network. We also looked at Istio, which is the most popular control plane here. We evaluated it both in running it in a self-hosted mode or as a managed product like Solo or Anthos. And finally, like I said, we looked at extending the system we already had in place. And once we had picked our candidates, we did an assessment where we evaluated each candidate against the criteria we had laid out. And there's a lot in this slide. I don't expect you to read it all. I see you're squinting there in the back. But to summarize, I mean, for Traffic Director, since we already had some experience here, we kind of knew that it didn't quite meet our current needs. And additionally, the fact that it's only available in a managed mode, and it's a lockdown product. We had limited options to extend its functionality with features that we needed at Spotify. For Istio, our main concerns were around scalability and that certain critical features that we needed weren't available for the Proxyless gRPC mode of running Istio. And then finally, extending our own system, I mean, our hunch when going into this work was that this was going to be the most attractive option, and it tends to be for engineers, and we've all been there. And we would be building on a foundation that was proven to meet our scalability requirements and had been tailored to our service network from the start. So, unsurprisingly, when we weighed our options, we found that extending our system was the best option, yes. But even though we suspected that we would end up with this conclusion, it was still worth going through this evaluation process because it helped us understand which problems that we thought were most important for us to solve. And it was very appreciated by management, like Kalbir sitting over there, because they are naturally suspicious of engineering teams coming with proposals to spend a lot of time building infrastructure in-house. And I also wanted to point out that we did this evaluation a bit more than a year ago, and I know that there have been many relevant improvements in all the products that we evaluated since then, so it might be like that this table would look different if we did this evaluation today. But anyway, with that in place, we were excited to ship some improvements. And the first fundamental deliverable we had was to introduce a new protocol to manage the data plane. And as mentioned a few slides back, DNS was too limiting. And one of the must-haves in our evaluation was the ability to use XDS to configure our Proxyless gRPC fleet. So XDS is a universal data plane API. It's spun off from the Envoy proxy project, and it's supported natively in gRPC and Envoy, meaning that if our control plane supports this protocol, we can easily integrate Envoys and gRPC services into the mesh that we're building. And we have a prior experience using XDS for our Envoy-based perimeter that we've been operating for 5 or 6 years. It has a good feature set that meets our needs, and using XDS as a foundation would let us then build out the prioritized features that we had without much hassle. And now just briefly go over 3 of the features that we have built or are in the process of rolling out. First up is traffic splitting. So we needed the ability to divert traffic based on rules. There's a pilot use case at Spotify where a team needed to divert synthetic traffic that was used, I think, for some ML training or something. But they needed to separate that from real production traffic at multiple points in the call chain. And solving that in the application layer would have meant, code duplication and then changing these rules and working with this would have meant, changes that would span several systems and services, which would have been very cumbersome to work with. So instead, we solved this in the network layer by implementing an imperative API that the pilot team was then able to use to add custom matching rules and gRPC routes, which were then automatically pushed out to the relevant clients using XDS. Next up is my favorite, zone-aware routing. So in each GCP region that Spotify is running, we usually run in 3 or 4 availability zones due to our size mostly. But our service network is really not zone-aware. It's an artifact from the on-prem days. So our failure domain is still regional, which means that we're not really taking any advantage of being deployed in multiple availability zones. Like if one zone were to have troubles, we would need to drain the whole region anyway. And since sending traffic across the zonal boundary costs money, we want it to be routed as much as possible within the same zone. And to do this safely, the control plane then needs to account for uneven spread of server or client couplings between the zones. And the server locality part of the server's locality is already part of the Kubernetes endpoint. And when we use XDS in the client, that means that we have a persistent connection to each client, which then lets us also know what are the clients that are calling each service and how they are distributed across zones. And with this information, then we're able to build a zone-aware load balancer and we use the Envoy Proxyless locality-aware load balancing algorithm as a base. And then we factored in data from cluster load reports, which is another XDS feature, to account for differences in throughput between clients. And this load balancing policy is now replacing a less effective mitigation we have to keep traffic within the same zone. And we can talk more about this after the talk. It's my favorite topic. Anyway, thirdly, the third feature that we built, or rather got for free, was this dependency graph. Since the new architecture has a connection to every client and we have every server in our service discovery dataset already, we can easily dump a dataset with a global view of what's connected to what. And with the later addition of load report data, we're going to also be able to show how traffic flows between services in real time or dumped into a dataset. Yes. And now I'm handing over to Erika to talk a bit about how we built this.
Yep. All right, so the first thing we asked ourselves was where in the current design of Nameless XDS would fit. This diagram here shows how endpoints register themselves with Nameless. So workloads that run on VMs send periodic heartbeats to a component called Nameless registry. And the corresponding service discovery data is then stored in a spanner database. For workloads that run on Kubernetes, there's a component called Shameless, as Erik mentioned before, that on startup will connect to all of the clusters in that region and creates watches for endpoint slice resources. From there, it stores any service discovery data in memory, and over time, it updates it according to the change events that it's notified about. DNS lookups come in from core DNS. And this in turn forwards to another component called Nameless Discovery. So service discovery data lives in 3 different places. We have a spanner database, we have Shameless for Kubernetes workloads, and we also have Cloud Data Store, which holds configuration for redirecting traffic to other regions for services. So Nameless Discovery basically looks in all of these places to put together the correct answer to for every DNS lookup that it's forwarded by core DNS. So again, given this setup, where would XDS fit? So we considered a few options, each of them optimizing for something different. And in the end, we settled for option number 3, which combines adding XDS to Nameless with a larger initiative to revamp its tech stack and its design. And we'll see exactly how in the next slides. An objective of ours was to move fast through development cycles without disrupting the current production traffic. So we deployed the revamped Nameless as a separate system. We also built a new deployment pipeline that would allow us to have deployments that are basically safe, quick, and hands-off completely. And this is powered by Argo CD and Argo rollouts. And only at this point, we then went ahead and built XDS capabilities into Nameless. Once all of this development work was complete, we gradually migrated production traffic from, let's say, the old system over to the new one. And note that at this point, all of the clients were still using DNS as a protocol for service discovery. Once the redesigned Nameless proved to be stable, we then started onboarding clients onto XDS. But let's now look at the new design. All right, so first off, we changed runtime from VMs to Kubernetes, so now we have a Nameless pod instead of a Nameless VM. Workloads that run in Kubernetes register themselves just like before, nothing has changed there. Workloads that run on VMs still send periodic heartbeats to Nameless registry, but now this calls out to Shameless, and Shameless, via the Kubernetes API server, writes a bunch of CRDs into etcd to store the relevant service discovery data. Shameless also creates watches for the CRDs, storing the service discovery data in memory and updating it as it receives change events over time. A similar flow is also in place for the configuration that allows service owners to redirect traffic to another region for their service. Core DNS, of course, is still there, but now it forwards to Shameless, which can answer correctly by just simply looking into its in-memory store of service discovery data. So we have a simplified design. Because the data is no longer scattered across different places, Nameless discovery is completely gone from the picture, and so are Spanner and Cloud Data Store. And a nice effect of all this redesign is that latency of DNS queries has gone down significantly because, of course, in-memory lookups are cheap. And now with this new design, the answer to the question, where does XDS fit, became a bit more obvious. Shameless has the complete picture of the service discovery data at all times and already answers DNS lookups. So it seems like the most logical place where to add our XDS interface. All right, before we move on, let's just go quickly through a refresher on XDS. So XDS stands for X Discovery Service, where the X indicates an arbitrary resource. It's a set of APIs that is used by a data plane to understand how it should configure itself. And the configuration comes from a control plane in the form of resources of different types. One possible setup is to have individual APIs implemented on the control plane side, each providing specific configuration resources. The client then fetches them over separate gRPC streams. An alternative setup is that the control plane instead implements something called ADS, which stands for Aggregated Discovery Service, and the client then fetches configuration of all of the types over one gRPC stream. But back to our story now. So initially, when we began, we thought that we could just simply rely on an Envoy's open source library called Java Control Plane. So straight away, we started building a POC. They used this library, but soon came to a stop. In the case of a proxyless gRPC service mesh, each node can have multiple gRPC channels to the control plane, specifically one per service that that node wants to talk to. And each of these channels maps in turn to a series of configuration resources that the node subscribes to. And when one of these resources changes, the control plane has to be able to push updates to all of the nodes in the mesh that have subscribed to it. So to do this correctly, the control plane needs to remember every individual gRPC channel from every node and the configuration resources relevant to each of those channels. The open source library simply didn't give us that level of control, so again, what to do? We considered a couple of options. Forking the open source library, maybe extend it to somehow fit our use case, or second option, just implement XDS ourselves from scratch. And it didn't take us very long to decide for option 2. And for us, it's been a good decision, after all, for a couple of reasons. First of all, we could optimize for the most important thing. So our focus is to build a proxyless gRPC service mesh. So we implemented XDS specifically with proxyless gRPC clients in mind. Effectively, that meant implementing ADS state-of-the-art variant of the XDS protocol, which didn't take us too long to do. A second benefit of all of this is that we have full control over this implementation. So in the future, if the need arises, we can extend it to support other types of XDS clients. We could also instrument it to fit our observability requirements exactly. And finally, we could start simple and just hold off on any premature optimizations. And if bottlenecks emerged when we scale this out to many services, then we would address them at that point. Of course, implementing XDS from scratch also came with some challenges. No formal protocol specification exists, even though there are some extensive Envoy docs on how the protocol works. So many times for the finer details or edge cases, we refer to other implementations, for example, the Istio code base. And especially at the beginning, we assumed that we would end up with a ton of super complicated code to reason about and to maintain. But it turns out that it's relatively little amount of code, and it's also relatively not obscure to reason through. With our XDS implementation in place, we then turned to onboarding services onto XDS. And we started by laying out some non-negotiable requirements for the rollout. So first of all, no big bang or YOLO rollout for this, because it's too risky for such a big change. We want to be in control of which and how many services switch to XDS through configuration. And in particular, we want to control groups of services that are eligible for XDS based on their metadata. But also, we want to control what percentage of any given group will actually switch to using XDS. So to give you an idea, an example configuration would be 10% of services that run in region Europe, blah, blah, whatever, and have reliability tier 4, meaning they are less critical services. Another requirement of ours was that no intervention from service owners was required. Also, we aim for zero disruption, or in any case, minimal disruption. And last but not least, we want a nice big panic button that takes us back to a known good state quickly. So let's see how we actually rolled out XDS. So all of the gRPC services at Spotify use an in-house managed Java framework, which is called Apollo. Apollo provides gRPC-specific modules to do things like start up a gRPC server or make outgoing gRPC calls to other services. For lower-level things, the framework relies on a library, an in-house Java library. You can think of this as a wrapper around the open-source gRPC Java, containing some specific Spotify logic. So to roll out XDS, we changed both of these pieces. First off, we created a custom managed channel in the gRPC client module of Apollo. This behind the scenes maintains two open gRPC channels, one for DNS and one for XDS. It also runs a task in the background periodically that reads the value of a global flag, indicating whether XDS is currently enabled or not. We use a DNS TXT record for this. And depending on the value of this flag, then either the gRPC channel for DNS is used or the one for XDS. And this that I just described is effectively what powers our fallback procedure to DNS. Also, when a gRPC service boots up, something that we call XDS eligibility checker determines if that specific service should use this new managed channel or just the standard regular one. It does so by comparing the service's metadata against the current configuration of the XDS rollout. If the service is deemed eligible to use XDS, then we also need to configure the XDS client that runs inside gRPC so that it knows which control plane to talk to. So it's configured to talk to Shameless in our case, and to send over metadata to identify itself to the server. And for this, we wrote some XDS bootstrapping logic that puts together the right configuration at runtime and dumps it into a system property. From there, the configuration is read by the XDS client so that it knows who to talk to. All right, so once all the pieces that I just talked about were in place, we started onboarding services onto XDS. We initially just targeted a group of less critical services and went slow, especially at the beginning, by configuring a small percentage of the group in just one region. As a next step, we went for 100% of that group in the same region. And then in 3 different increments, we onboarded the same group in all of the other regions. To give you an idea, this initial phase took us approximately a month and a half, and saw a few hundred distinct services using XDS instead of DNS for service discovery. We then targeted a new group of services, this time a bit more critical, and we moved through this group faster, onboarding larger percentages globally. And from there, we're just rinsing and repeat, basically until we run out of groups of services to onboard. But let's see how it's going. So definitely rolling out XDS gradually and in a controlled way has been the right choice. Going slow at first and targeting only less critical services allowed for bugs and different types of issues to emerge without causing outages for Spotify users. Also, seeing hundreds of services using XDS and working just fine gave us confidence to push through and then onboard more critical things. Something else that proved very useful is our beloved panic button, because with it comes peace of mind for the engineers that are doing all of this work. At any time, we can have all of the services switch back to XDS in a matter of 3 to 4 minutes. And that also means we can troubleshoot issues at leisure, free from the pressure that comes inevitably during an outage or an incident. It's also a very simple procedure, easy to operate and to reason about, and that's greatly appreciated, especially when you're on call for this stuff through the night. All we need to do, if we're paged at 2 a.m., is reconfigure the value of a DNS record and just then watch some graphs. And finally, it's also kind of neat that to fall back to DNS, we're using DNS. But of course, there were also some challenges. So let's talk through some of those. So lots of moving parts create complexity, of course, and complexity is a pain most of the time. Admittedly, some of this pain is self-inflicted because our decision to revamp Nameless meant that for a while we had to maintain 2 separate systems and to operate them for service discovery. But also complexity comes from big initiatives that are led by other infra teams at Spotify, which can make things tricky to navigate at times. Sometimes it has also been difficult to pinpoint issues when services started using XDS. So typically a problem would pop up in 1 or 2 services while hundreds of others were working just fine. So from there, it would be a bit of a game of spot the difference to understand how the affected services were in some way different from the rest. And also in some cases, it was difficult to reproduce issues outside of the impacted services, which slowed us down a bit. Obviously, we had our fair share of bugs in there, and some of the assumptions we made during development turned out to be incorrect. One issue in particular that I want to mention is that generating the XDS bootstrapping configuration at runtime has proven flaky, and a couple of services ran into some XDS initialization problems. So as a stopgap solution, we make sure that we run that logic as early as possible in our managed Java framework Apollo. But in the long term, we want to switch to have this logic happen ahead of the Java service running, for example, via an init container. And finally, rolling out XDS has sometimes been about educating service owners. They came to us convinced that XDS had broken their service when in reality it surfaced pre-existing issues with some services, like not having zero downtime deployments. So what is next for us? Well, we have a bunch of ideas about features that we could add next to our service mesh, and I listed them here. But most likely, before jumping too deep into any of these features, we'll do some thinking around how we can extend our service mesh to cover more of the Spotify service network. So our focus so far has been on gRPC Java services specifically, but definitely moving forward, we want to support other protocols and other languages as well. All right, so now it's back to Erik for some concluding thoughts.
Thank you. Right, so to conclude, did XDS deliver? The protocol itself is fairly straightforward. Like Erika mentioned, the implementation part only took us a few weeks. And then after that, we were able to move really fast on new feature development on our new XDS-powered stack. But because running XDS and Proxyless gRPC is quite uncommon still, there's very little publicly available information and guidance, which did slow us down a bit. And would we recommend what we did to others? And yeah, it depends. It's a classic answer, right? It's a flexible and powerful protocol, XDS, but it might take a bit of engineering effort to integrate into existing systems. But it's been a really good fit for us, and we hope that this talk will inspire some of you to try it out. And we're very interested in talking more and sharing more learnings about Proxyless gRPC or XDS with peer companies. So if you work for such a company, or you just want to talk about this stuff, then please reach out to us now after the talk or over an email. We're around the conference here until tomorrow. Otherwise, you can always send us mail here. And yeah, thank you.